Okay, this is the first video on sample proportions, and we're going to be introducing proportions and hypothesis tests. And a lot of this you're going to need to read on your own. This is page 172 or numbered page 172, and you do need to read this material. But beginning with what you need to know. Central limit theorem states that the sampling distribution of the expected value of means will become normal if the sample is large enough. And we always said if n was greater than or equal to 30, then the distribution of the x bars became normal. And this is what we had. Now, basically, all that's really referring to is the fact that we could use a formula that looked something like this: x bar minus mu sigma divided by the square root of n. And we also said t equals x bar minus mu s divided by square root of n. So that's all that's really saying, that this is our standard deviation. If we use a sample standard deviation, this is our sample. If we use a population, and we're working with a distribution of means. But the requirement was that we needed a sample size of 30 or more to be large enough, or the underlying population had to be normal. When we're working with proportions, we have essentially the same thing. Our formula is going to look a lot different, but we need to make sure that we have the sample is large enough. And so we're going to actually be working with some conditions. Now, the first condition is random sample, and you're not going to need to write that down. You also need to know that n is less than 10% of the population. We're not going to check that one either. But the one that you need to put a star by and make sure you're aware of is we need to make sure that our sample size times our proportion is greater than or equal to 10, and n times q, where q is just 1 minus p, is also greater than or equal to 10. So you'll need to check this one. This is one that you're going to have to do every single time to make sure that it's large enough. The rest of them, you're not going to worry too much about. Now, we have a different formula. In the past, we were working with z equals x bar minus mu sigma divided by the square root of n. That's what we had. Well, we're going to change that up, and p hat is going to be our sample proportion, whereas x bar was our sample mean. P is our population proportion, whereas mu is our population mean. So that's how they're related. And then underneath the radical is just completely different. This is the proportion. This is 1 minus the proportion divided by n. Now, you'll need to write this formula down. You'll need to plug the numbers in, but the calculator does the actual work. So what does P and P hat equal? P hat equals x divided by n. X is the number of successes, n is the sample size. All right, that's all it is. And it's not that big of a deal. Once again, here's our standard deviation. Now, this is the one that you need to use for a hypothesis test. Really important to note this. This is the one you'll be using for a hypothesis test. And notice that I'm using the actual claimed value. So this is the population proportion. Now, it gets a little tricky here because for confidence intervals, it's going to be a little bit different. We're going to need to use the sample proportion. So population proportion, this is what was claimed. That'll be like our null statement. And this will be our sample proportion. This is what we got from the sample. All right. We're going to skip this. We would do this in a non-COVID year, but this is a COVID year, we're not going to do it. You can read all this material, but I don't think any of this is going to be a surprise. Obviously, if it's not equal, it's a two-tail. If it's a greater than, it's a one-tail upper. If it's a less than, it's a one-tail lower. That's generally what is said here, but please make sure you're familiar with it. Your recipe for success: start off by writing the null hypothesis. And you'll say P naught. You can just say P, but I'd rather you say P naught. You can just say this, but I'd rather say P naught. P naught equals, or P equals, and you're going to have the alternative is going to be not equal to, less than, or greater than. So nothing new there. We're going to define this in context, and this is going to be let P equal the true population, and wait for it, proportion. All right, and then of whatever. The ones you're going to have to do on conditions, you have to do this to show normality. These two must be greater than or equal to 10. And a lot of times I just give it straight out to you as a number, and you'll see that in just a moment. Here's our formula. This is the sample. This is the pop or the claim or the hoe. And notice we use the hoe down here. All right. As far as our conclusion, sounds just like everything else we've been doing. Our p-value is this. There's sufficient evidence, et cetera, et cetera. So no real big difference. So let's get on to working one of the problems. So a union spokesman claims that 75% of union members will support a strike if their basic demands are not met. This is a claim. This sounds like this might be our null hypothesis, but let's keep reading. A company negotiator believes the true population, the true percentage is lower and runs a hypothesis test at the 10% significance level. What is the conclusion if 87 out of a simple random sample of 125 union members say they will strike? All right, so we have a claim. So our null hypothesis is HO, P equals 0.75, P or P naught, HA, P, and they say believes that it's lower. So that's what they're checking to see if it's lower. P is less than 0.75. So next thing we need to do is we need to define our parameter in context. So let P equal the true population proportion of union members who will strike. In other words, they're claiming it's 75%, but someone doesn't believe it, so we're going to check it out. All right. So the next thing we need to do is write our conditions. Well, we're not going to worry about anything but the NP and NQ being greater than 10. Well, before we do that, let's find P hat, just because I think that's going to help us out with understanding this. So P hat equals X over N. Well, in this case, 87 out of 125 are going to strike. That's what we ended up with our sample. So 87 divided by 125 equals 0.696. So that's our P hat. So we need to check to make sure that our sample is large enough, and to do that, we're going to have to go N times P hat. All right, N times P hat, and that number is going to have to be greater than 10. Well, what was N? Well, N's 125. So 125 times 0.696 equals, well, we already have that, equals 87. That's greater than 10. So first condition was met. So we need NP, so that's NP hat greater than 10. We also need NQ hat greater than 10. And Q hat is just 1 minus P hat. All right. So in this case, we're going to go, well, in 125. Q hat is going to be 1 minus 0.696. 1 minus 0.696. 1 minus 0.696 times the 125. We end up getting 38. And that's also greater than or equal to 10. Second condition met, we can move on. Now, one thing I want to point out to you real quickly is we could have sat there and go, you know what? We have 87, 87 greater than 10, we're good to go. We didn't have to multiply this time. Sometimes you do, sometimes you don't. But basically, if you're not sure what to do, calculate p hat, because you're going to have to do it anyway. Calculate p hat and multiply by the sample size. And it's like, oh, it's greater than 10. 1 minus p hat is 38. Now, I could have just gone, in this case, 125 minus 87, and I would have been good to go. All right. Anyway, both are greater than 10, so we are good to go. So I need to go ahead and write my equation. Well, my equation for proportion is z equals p hat minus p naught, q naught, n. All right, now I can start plugging in. Well, we already calculated p hat, so this is going to be 0.696 minus the 0.75 over, now be real careful, this is where it's easy to make a mistake. These values have to be the same. So this is going to be 0.75, this is going to be 0.25, and my sample size was 125. Okay, so we've gone ahead and we've done all that work. So now we can run to the calculator. And the calculator is going to do a nice job for us. It's going to go stat test. And we're going to look for one proportion z test, which I guess is number 5 on your calculator. And the first thing it asked for was p naught. Well, p naught was 0.75. X. Oh, that was the number of successes, which was 87. N was our sample size, 125. And we said in our alternative that we wanted a less than, so I need to make sure I have a less than highlighted. And I end up getting the probability that z is less than negative 1.39 equals 0.0816. This is my p-value. And they gave us an alpha of 0.10. Because they said 10% significance level up here. All right. I'm using 10%. This is less than. So our decision is we reject the null. So we're going to go ahead and start writing this out. We're going to start writing our conclusion. Our p-value is 0.0816. We reject the null. There is sufficient. In other words, there's plenty of evidence. We have enough. There is sufficient evidence at alpha equal 0.10 to suggest that the true population, we're not working with the mean, we're now working with the proportions. We have to say proportion, key word right here, true population proportion of, how did we define it? Of union members who will strike is less than 75%. And if you prefer, less than 0.75, either one, but I rather write less than 75%. So in other words, based on this, we don't believe the 75% is a true value. We believe it's going to be less than that. we got a sample size 69.6%, so it's under 70%. But we believe it's going to, so if someone asks you, do you believe them? You're going to say, no, we believe it's less than 75%. That's all we're going to say. We're not going to say what it is. We're just say, no, it's less than 75%. It says explain the meaning of the p-value in context and a type of error. We're going to skip this part just because it's a COVID year, but the type of error, well, we rejected. All right, we rejected. So the only type of error would be type 1. All right, so we might have been a type 1. Might be a type 1. Definitely not a type 2. All right, we probably should say that. Can't be a type 2. Cannot be a type 2. Because we're not sure if we made an error. So it might be a type 1, cannot be a type 2. We can only get a type 2 if we fail to reject. All right, that concludes this video. Thank you.